Good afternoon, everyone, and welcome to this week's Zoom for Thought Talk, during which Brian will tell us about multisymplectic variational integrators for Hamiltonian PDEs. Thank you for coming, Brian. Take it away.
Cool. Awesome. Thanks for the intro. Okay, my name is Brian, and today I'm going to talk about multisymplectic variational integrators, which are a class of numerical methods which are used to model Hamiltonian PDEs, as my title suggests. So I think I'll just get right into it. Okay, so this is kind of an overview of the talk. First, I'm just going to give motivation for what the problem is that we're trying to address. And then I'm going to discuss some relevant background. The main points are, so we're trying to talk about Hamiltonian PDEs and how to model them. And in order to build up to that, we should first talk about Hamiltonian mechanics and the way we model those on a computer. And then I'll talk about how to think about Hamiltonian PDEs and some of the structures that we need to consider in order to be able to model these kind of problems appropriately. And so that's essentially going to be the first half of the talk, this background material. Sorry, can you see my mouse? Yeah. Maybe I should use a laser pointer.
We can see when you hover around.
Okay, well, in any case. And then after that, I'll talk about the main content of the work that we're doing, which is the variational integrators for this class of problems. Okay, and then I'll present some examples at the end. Okay, so just a quick talk about the motivation. So the idea behind this problem is discretization. So you start with a problem, a system that's described by an ODE or PDE. And as we all know, you generally can't solve many ODEs or PDEs exactly. So one of the things that we do is we model them on a computer. And so we take this problem, which has generally infinitely many degrees of freedom, and then reduce it to a system that's approximately close to our original system that only has finitely many degrees of freedom. And because it has finitely many, you can solve that problem on a computer. So the main issue, though, is that when you approximate this system by this one that you can actually solve, you want to know that the solution of your approximate problem in some sense converges to the actual solution, maybe in the weak sense or some norm topology or something. So that's like the basic goal behind discretization. But there's another goal, which is to say, if your problem has some inherent structures to it, and you just apply any arbitrary discretization, you might lose those structures. So for example, if you have a Hamiltonian system in mechanics, and you just apply, let's say, like RK45, like a common ODE solver in MATLAB, your discrete system won't preserve the symplectic structure inherent to your Hamiltonian system. So hopefully by the end of this talk, I can kind of convince you that if you have some system with structure, it's a pretty good idea to at least consider what's happening to that structure when you discretize the system. Okay, so what do I mean by structure is, of course, this varies on the problem that you're considering. The problems I'm going to talk about today are field theories arising in like mathematical physics. So the relevant structures there would be like the variational structures, symplectic and multisymplectic structures, structures relating to symmetries and conservation laws, just like Noether's theorem, and then also algebraic structures such as Poisson structures. So the kind of, the motif behind structure preservation is if your continuum theory has these, in some sense, your discrete theory should have these as well. And you get a lot of nice things for free, like, well, I guess not necessarily for free, but you get a lot of nice things when you preserve these structures. One of the main things that you get are discrete objects, which essentially are pullbacks of the continuum objects. Like if you appropriately define some discretization map, and you view these discrete objects as pullbacks of the continuum ones, and you also get some nice things like variational error analysis, which I'll talk a little about later. Okay, so that's kind of the goal that we're headed towards. Okay, so the first bit of background is just how to think about classical mechanics. So we think about a mechanical system on phase space, which for now let's just think about as Rn times Rn. where the first coordinate is like the position Q and the second coordinate is the momenta P. And Hamilton's equations in mechanics say that if you have some Hamiltonian, which is just some smooth function on the space, which you can think about as the energy, then the system evolves under these equations. Q dot equals dH dP, P dot equals minus dH dQ. So the classical example is if you take Hamiltonian, which is kinetic energy P squared over 2m plus potential energy V of Q, and you plug it into these equations and you eliminate the momenta variables, you just get Newton's second law, right? Which is mass times acceleration is minus the gradient of the potential, which is the same as the force. Okay, so that's yeah, the usual example. We can write this these two equations more succinctly if we concatenate these position and momenta variables. And so we can write it in the following form: J z dot is equal to the gradient of h with respect to z, where here J is a 2n by 2n skew symmetric matrix. Okay, so this is kind of the coordinate version of Hamilton's equations. We can define this more intrinsically if we use symplectic geometry. So we assume that we have a symplectic manifold m comma omega, which is manifold with a closed non-degenerate 2 form. And in this setting, Hamilton's equations state that the system evolves under the flow of this Hamiltonian vector field. Let's see if my pen works. Oh, sorry. Okay, so this is the Hamiltonian vector field xh, and it's defined by this equation ixh omega equals minus dh. Because the 2 form omega is non-degenerate, it defines a bundle isomorphism between the tangent and the cotangent bundles. So this xh, emits a unique solution for a given choice of Hamiltonian. Okay, and then the simplest case is if you take your symplectic manifold to be the cotangent bundle, and then your symplectic form to be the canonical symplectic form on the cotangent bundle, then it precisely reproduces the above example of classical mechanics. Okay, so some immediately nice things about formulating it geometrically is that you can immediately prove some pretty nice properties of your system. So one is energy conservation. So that's to say that the Hamiltonian is preserved under the flow of the Hamiltonian vector field. So here phi sub t denotes the time t flow of the Hamiltonian vector field. And you can pretty easily prove that the time derivative of this quantity is 0. And that just owes to the fact that the symplectic form is skew symmetric. So when you evaluate on these with the 2 same inputs, you get 0. Okay, and then another nice property is symplecticity. So if you pull back the symplectic form by the flow map, you get the exact same symplectic form. So the symplectic form is preserved under this flow. And we'll think about this as preservation of area in phase space. So I'll show some plots of that later. And then finally, another nice property of these systems is Noether's theorem, which says that if you have a symmetry, so a symmetry group which acts by symplectomorphisms on your symplectic manifold and also preserves the Hamiltonian, then you get a conservation law. And that implication actually goes both ways. So a conservation law also generates a symmetry. Okay. So the kind of goal in like discrete mechanics is to take some Hamiltonian system that you have and discretize it, so that generally consists of a map. Let's say, why is my pen? Sorry. So this consists of a map taking your momenta and position at some time to your position and momenta at another time, and you want to construct a map such that it preserves the symplectic form. So such that you have this relation right here. Okay, so here I'm using like the canonical symplectic form on the cotangent bundle. Maybe up to a -9, but all right, so we'll just consider the canonical case. And so you might ask, how would you construct a symplectic integrator? So traditionally, these were constructed by looking at various numerical ODE methods, such as Runge-Kutta methods, and kind of constructing them in an ad hoc manner, saying, what conditions you would need on the Runge-Kutta coefficients in order to get a symplectic integrator. But recently, there's been a new class of integrators on the Hamiltonian side called variational integrators. And the idea is you take a continuum variational principle, which I'll talk about in a second. You discretize that into a lattice. So instead of looking at like the continuum variational principle over curves, you only look at it on a discrete set of points. And then you enforce the variational principle here. And it turns out that when you do this, you automatically get a symplectic integrator. Okay, so instead of trying to construct symplectic integrators in an ad hoc manner, if you just reduce the variational principle, you actually get these symplectic integrators directly. Okay, so why do we want to consider such symplectic integrators? So the following is a set of plots for some Hamiltonian system whose phase lines are shown here on the left. And because it's a Hamiltonian system, the flow should be symplectic, which means if you start with an initial collection of particles in phase space and you flow it under the evolution of the system, the area of that collection of particles should be preserved, right? It can be, stretched as it kind of shows here on the left, but the area is still the same. Okay. So if you compare various methods, you'll see different results. Okay, so on the right-hand side, here at the top left, we have the explicit Euler method, and the explicit Euler method is not symplectic, right? So if you look at these pictures of these cats, you'll see that they start growing, right? And this isn't too surprising because if you're familiar with the explicit Euler method, you'll know that it's unstable and it causes like solutions to grow exponentially. Okay, so that's not too surprising. The implicit Euler method, which also isn't symplectic, it's a stable method, but the reason it's stable is that essentially it always collapses solutions down, right? So it damps solutions down. So here it causes the area to shrink, right? And then in contrast, the symplectic Euler method preserves the area of the phase space. Okay, and the kind of interesting thing about the comparison on the left is these are all the same order method. So they're all order 1 methods. So even though they have the same local error, when you patch things up globally, the symplectic method performs better. Okay, and hopefully I'll try to explain why that is in a bit. Okay, and then on the right side, we just have a similar comparison with second order methods. Okay, any questions? Okay. All right, so symplectic integrators have been extensively studied in the literature, and they've been shown to provide very physically faithful models of mechanical systems. So in these plots, the left is simulation of the inner solar system from JPL, NASA and JPL. And then the right is a similar simulation just produced from like a run-of-the-mill symplectic integrator. And what they found in this paper, my advisor's paper, is that like the dynamics match extremely well. And the interesting thing about the simulation on the right-hand side was that they took time steps on the order of 100 days, which is extremely huge, right? Like, so normally you want to take time steps that are smaller than the dynamical scale set by your system. So in this case, like if Mercury has an 88-day orbital period, in general, you would want to take time steps smaller than that to resolve that scale. But symplectic integrators can resolve it even with large time steps. So that's what we mean by robust. Okay. The reason why the symplectic integrators perform this well in terms of long time evolution is that what you can actually show is that if you have a symplectic integrator, it doesn't actually sample the exact solution, but it samples the exact solution of a Hamiltonian system for a perturbed Hamiltonian. So it doesn't sample for the Hamiltonian that you want, but it samples it for a nearby Hamiltonian. And what you can show is that that nearby Hamiltonian is actually boundedly close to the actual Hamiltonian for exponentially long times. Okay, so that's why these integrators are extremely robust. Okay. Okay, so
Actually,
now
Brian,
yeah.
If I glean, may I glean from what you just said that the general strategy is to approximate the Hamiltonian in a smart way and numerically?
No,
Okay.
sorry. So yeah. Let me try to repeat that. So what you can show is that so there's this theorem due to Gann-Marsden, which says that you can't have a both energy preserving and symplectic integrator without sampling the actual solution, like without actually having the exact solution curve. So there's no way your symplectic integrator can can correspond to the true Hamiltonian unless you know the exact solution, which defeats the purpose. So unless you have an already solved system, like some linear system or something. But what you can show is that when you have a symplectic integrator, it actually arises from sampling a perturbed Hamiltonian.
Okay, it's the other way. Right? I see.
Yeah. So we might not know the perturbed Hamiltonian explicitly, right? But what we do know is that it's somehow close to the actual Hamiltonian.
Okay, sweet.
And then that's what explains this robustness. Cool.
Nice.
Okay. Although what we'll see here is like the strategy for constructing these symplectic integrators is pretty similar to what you said, which is to somehow approximate the Hamiltonian. Okay. So more precisely, what we're going to do is we're going to approximate the type 2 generating function. So the type 2 generating function is a notion in mechanics that gives you the exact flow map. So normally you think of the flow map as a map between Q0, P0, the position of momenta at some time, to Q1, P1. Okay. But the type 2 generating function is kind of given by swapping some of those around. So instead, we're going to think about it as a map from Q0, P1 to Q1, P0. Okay. The reason type 1 generating functions aren't great in numerics is they don't work for degenerate systems. Okay. So that's kind of the reason you use type 2 generating functions. Okay. So essentially what we do is, I don't know why my pen's not. So what you do when you define an integrator is, so this is our type 2 generating function. And what we want to do is essentially invert this map for a map like this, right? From initial time to final time. And then proving that you can actually do this usually relies on some kind of implicit function theorem argument, right? But this is how we're going to think about the map. But really, when you implement it, so this is type 2. Okay, but really when you implement it, like this is what you want to solve for. Okay, and that's type 1. Okay, so what I've written on these top equations are like the exact type 2 generating function for the actual Hamiltonian. And the basic idea is that we want to discretize this exact generating function. So here, the exact generating function, you extremize over C2 curves from your time interval into the cotangent bundle. And then the basic idea is to choose some finite dimensional subspace of this. And so instead of extremizing over space of all C2 curves, which is infinite dimensional, you're just extremizing over a finite dimensional subspace. Okay, so what you get at the end of the day is something you can solve on the computer. Okay, so assuming you do this, you can construct a discrete type 2 generating functional and then apply the variational principle. Okay, and then what you get are a set of equations here, which define your integrator. Okay, so these two equations here are what are known as Hamiltonian variational integrators. Okay, and this was actually vetted pretty recently. It was 2011 by Liok and Zhang. So this, even Hamiltonian variational integrators for mechanics is still in its relative infancy. Okay, whereas the theory of symplectic integrators is much older, but specifically how to approach it variationally is a lot newer. Okay, so one of the nice results about this class of integrators is this variational error analysis result, which says that if you can approximate your generating function to order R and the Hamiltonian is, say, C1, then actually the discrete flow is order R as well. So instead of having to analyze like these numerical methods and doing Taylor expansions and seeing what the order of accuracy is, you only have to look at how well you're approximating your generating function, which just has to do with, functional analytic arguments about your approximating subspace. So it's actually an extremely nice result. Okay, and then I mentioned this before, when you construct your integrators this way variationally, you actually get symplecticity for free. So if you look at symplecticity in the continuum case, it follows from the fact that like, the squared second exterior derivative of your generating function is 0. Like you can show that that's equivalent to the fact that the symplectic form is preserved on their flow. And the proof for symplecticity for this variational integrator is the exact same. Okay, you look at d squared ht plus, where that's the discrete generating function. Okay, so that's another nice thing about this whole theory is like everything matches analogously to the continuum case. It's actually very natural. A lot of the proofs that you end up doing, just you kind of copy it from the continuum case. It's pretty nice. Okay, and then you also have a similar kind of result about a discrete Noether's theorem. Like if you have a symmetry of your discrete theory, then it gives you a conservation law, associated preserved momentum map. Okay, so I think that's all the material I wanted to talk about for mechanics. So before I go on, does anyone have questions?
Actually, what do you mean by d squared h equals 0? Because depending on which d you're talking about, that is always the case.
Yeah, that's correct.
Oh,
so
okay,
it's the exterior derivative. Yeah.
Okay.
Yes. So if you
I think I see
the
what you're saying now. Yeah.
So the arguments are here, right? So if you compute d squared this.
Yeah, I see. Okay.
Yeah. Exactly. Yeah.
Nice.
Yeah, and the nice thing is that when we talk about multisymplecticity, the multisymplectic conservation law is going to fall in the exact same way. Yeah. Okay. Moving on. Okay, so now I want to talk a little bit about how to think about classical field theory. So classical field theory is a generalization of mechanics where instead of our fibers, like the position and momenta, depending on time, we think about them as depending on space-time. Okay. So more precisely, if you want to think about it, you can think about your fields as sections of a bundle, and the bundle that you want to consider is like the first jet bundle over space-time. Okay. So, I mean, if you have questions about that, you can ask, but I'm going to keep things mostly in coordinates. Okay, so classical field theory states that the dynamics of a field are governed by a variational principle, very similar to mechanics, where instead of your action being some integral over time, it's an integral over space-time. Okay, and there's two kind of equivalent pictures of classical field theory. One is the Lagrangian picture, where you look at like this is space-time, this is the field value, and then this is the derivative of the field. And the stationarity condition gives you the Euler-Lagrange equations. And well, maybe I'll just write it partial mu like dl. Okay, so this is like the usual Euler-Lagrange equation. The other way to think about it is to, instead of thinking about, so in this Lagrangian picture, we somehow think of the derivative as like independent of the field. And I mean, that it's pretty sloppy notion, but to make it more precise, you use the geometry of the jet bundle, and you think of the fibers as independent. So you think about it as a fiber bundle over space-time instead of a fiber bundle over whatever this field lives in. Okay, but the other way to do it is the Hamiltonian picture, which is to say, to define a space of momenta that kind of represent the derivative of the field in some sense. Okay, so here instead of our action depending on just the field, it now depends on the field and the momenta. And when you enforce the variational principle, you get the de Donnerval equations, which I'll show in a later slide, so I won't write it here. But it's essentially like a first order decomposition of the Euler-Lagrange equations. Right? Like, so in the Euler-Lagrange equations, you'll end up getting like second derivative terms here. But in the Hamiltonian picture, it's decomposed into first order components. Okay, so this class of, yeah.
And just for emphasis, right, the picture is that you're now trying to do classical mechanics on the infinite dimensional manifold of fields, as opposed to a finite dimensional phase space.
Yeah, so that's actually a really good question. So later I'm going to talk about what the multisymplectic conservation law is. And there's kind of two ways to think about it. One way to think about multisymplecticity is like an infinite dimensional symplectic structure, right? So in that sense, like you can think about your fields as evolving in the cotangent bundle of some infinite dimensional field space.
Exactly.
Right. In terms of numerics, that's a pretty hard route to go. The nice thing about multisymplectic geometry is that actually everything's finite dimensional.
Oh, sure. Yeah. This is not like to be made rigorous, because that's the hard part, right? So we try to avoid that as much as possible, but conceptually that's the way it's
but yeah, in the numerics community, there's, I guess, these two branches. One is this infinite dimensional canonical perspective, and then this newer branch is about, well, like thinking about the multisymplectic structure a bit more.
Interesting. Okay.
Easily. Yeah.
Sweet. Thanks.
Okay. Yeah. So as we've seen, like the action and the variational principle are more fundamental than the equations of motion, right? So like if you're trying to construct some kind of integrator, you don't want to just take the equations of motion, apply some like finite difference scheme or whatever, because you might not preserve the relevant structures. So the better route to go is like to take the variational principle, reduce to a finite dimensional subspace, and then derive these discrete equations of motion, and you preserve the structure in that way. And you also see this in, for example, like quantum field theory. Like if you look at the path integral, the elements of the Feynman diagrams are all defined in terms of like the action and the variational principle, and not from the equations of motion. Okay, so in that sense, I'd say the variational principle and the action are fundamental. Okay, so now I'm going to talk about kind of the multisymplectic formulation of this class of theories. And I'm going to do it, like I said before, mostly in coordinates or trivial vector bundles. Okay, but you can see our paper if you want a more geometric version of that. Okay, so we're going to think about our fields as valued in some, so at each point we're going to think about them as valued in some vector space. So more precisely, the fields are a section of some vector bundle. And then we're going to think about the momenta as valued in the dual to that vector space. Okay, and notice that there's one for each space-time direction. Okay, so here mu is like the space-time index, right? So in classical mechanics, you only have one momenta because there's only time on the base manifold. But here we have one for each space-time direction. Okay, so this is what we're going to think about as a relevant bundle here. So X is space-time, Q is where the fields are valued, and then the dual of Q is where the momenta are valued. And so we have one copy for each momenta. Okay, so this is a trivial vector bundle, but you know, for general theories, it's not, but I'm just assuming everything's trivial here. Okay, so a Hamiltonian is going to be just some function over this bundle. And with that, we can form the action. Okay. So if you look at this action, this is similar to the mechanics one, which was like the integral over some interval of the momenta p times the time derivative. Well, I guess it's not, it was q before. Time derivative of the position minus h of qp. Okay, integrate over time. So this is just an analogous generalization of that to higher dimension base manifold. You have this contraction between the two indices, so you're summing over them. So it's like P0 partial 0 phi. So that kind of corresponds to what we saw before, but then we have more terms because we're in higher dimensional space-time. Okay, and so if you apply the variational principle, you get these equations, which are known as the de Donnerville equations. And these equations I mentioned before are like the first order decomposition to the Euler-Lagrange equations. Because if you think of this momenta P mu as arising from a Legendre transform, okay, and then substitute that into this first equation, you essentially get the Euler-Lagrange equations. And then the second equation is like the inverse Legendre transform. Okay, so
Hey, Brian,
a simple, yeah.
how should I think of these multi-momenta conceptually? Because like I kind of know what a momentum is physically when you have
So
one.
in classical mechanics, right, a momenta by definition is like the derivative of the Lagrangian with respect to the velocity. And so sorry, not v dot, just v, or let's say q dot. So usually when your Lagrangian is like quadratic in the velocities, like 1/2 q dot squared, then p is just equal to q dot, maybe with a factor of m in front.
Yeah.
So like they're equal up to a constant. And so you should think of it the same way in space-time, except that your field now has more than just a time derivative, right? It has a derivative.
That's what you're saying. Okay. I see. Great.
Yeah.
Thank you.
So like, for example, this example that I have here, the nonlinear Poisson wave equation, you take some Hamiltonian, which is quadratic in the momenta, and then you have some potential term. So this think about as the kinetic energy, and then this is the potential. And then what we see from the de Donnerville equations is that we have one momenta corresponding to each space-time derivative of the field. Okay. So in essence, like, you know, when you have like a second order PDE and you write it in first order form by introducing like each of the derivatives as their own coordinate, essentially. So this is essentially doing that. It's just turning the second order problem into a first order problem.
Yeah, that makes sense.
Okay. All right, so yeah, if you look at this example and you compute the de Donnerville equations and then you eliminate the momenta, you just get the nonlinear Poisson or wave equation, where whether it's the Poisson or wave equation depends on if you're using like a Riemannian or the Lorentzian metric. Okay, so now the de Donnerville equations, which is stated on the last slide, can be written in the following skew symmetric form. So you have k mu partial mu z is equal to the gradient of the Hamiltonian, where z is like the concatenation of the field and the momenta variables. So this equation generalizes the one we saw in mechanics, right? So in mechanics, we had like j partial 0 z is equal to the gradient of h, right? And so now we just have, on the left-hand side, we have one of these for each space-time direction. Okay, so this is like the classical form of a multisymplectic Hamiltonian system. Okay, so and any Hamiltonian PDE can be expressed in this form. All right. Okay, and so to each one of these skew symmetric matrices K mu, we're going to associate a presymplectic two form, right? Which is just given by the usual relation between like skew symmetric matrices and two forms, at least in coordinates. Okay. So this is kind of what it means for a theory to be multisymplectic, is that it emits multiple presymplectic forms, namely one for each space-time direction. It turns out that if you think about it a bit more geometrically, because I'm doing everything in coordinates, but these various, these multiple presymplectic forms actually correspond to one single multisymplectic form. So a multisymplectic manifold is a manifold which emits a closed non-degenerate K form, right? Where now K can be any number, not necessarily two. Okay, so it's like a clear generalization of symplectic geometry. And it turns out that like these n+1 presymplectic 2 forms are actually the coordinate decomposition of some larger multisymplectic form, where the relevant multisymplectic manifold is like this the space where these fields and momenta live, the dual jet bundle. Okay, so when you have such a Hamiltonian system, what you'll find is that it emits this conservation law here, which is called the multisymplectic conservation law, or the multisymplectic form formula. And you'll see that it's very similar in form to symplecticity. So in a few ways. So first of all, symplecticity, you can state as like the integral over the boundary of some time interval of your symplectic form is 0, because that essentially means like when you evaluate over the boundary, you just get like the symplectic form at one time minus the symplectic form at the other time, right? Where the minus sign comes from the induced orientation on the boundary. Okay, so in that sense, it's a clear generalization of symplectic conservation law. Okay, so I stated that here, but it also generalizes it in a different sense, and this is the question Baki brought up earlier, which is how to think about like kind of the infinite dimensional symplectic geometry. And if you take some space-time cylinder, which looks like an interval across some region in space-time where the boundary of that region is 0, then multisymplecticity actually becomes symplecticity of the first symplectic form that you define. So the symplectic form corresponding to the time coordinate. Okay, so this is like the infinite dimensional field theoretic symplecticity. So the multisymplecticity also reduces to symplecticity when you integrate over a specific type of region. Okay, and it also encodes various other kinds of conservation laws, such as reciprocity and conservation of wave action. So the notion of multisymplecticity is, I don't think it's that well understood yet. I mean, we understand that it reproduces symplecticity, it gives some kind of canonical notion of symplecticity, but the actual implications of the geometry isn't that well understood yet, at least based on my understanding. Okay, and we have similar kind of like Noether's theorems as we saw in mechanics. Okay, all right. So before we talked about what it means for a discrete method to be symplectic, which is that somehow the symplectic conservation law is preserved at the discrete level, and we're going to define it analogously in the multisymplectic case. So this was like the traditional definition of a multisymplectic integrator, which is to say, when you discretize the following system, right? So you discretize the Hamiltonian system using some numerical method. And how do you do that? You replace like partial mu by some finite difference operators. Partial mu I0 to IN. So here the indices I0 to IN like describe the lattice that you've discretized your space-time region on. Okay. So assuming you do this, you get some numerical method, right, which is given here. And then we define a numerical method given this way to be multisymplectic if also the multisymplectic conservation law holds with these same difference operators. Okay, so like we replace these with finite difference, and a method is multisymplectic if it also holds that this conservation law holds with these derivatives replaced by the same finite difference operators. Okay, so it's a very ad hoc definition of multisymplecticity, and it also requires two pretty restrictive assumptions. One is that you're using a rectangular grid, and then the other one that you're using finite difference operators. And finite difference operators aren't the only way to discretize the PDE. Like there's like finite element, finite volume. So somehow this notion is both ad hoc and pretty restrictive already. Okay, so what we're going to show is that the way we derive it variationally, you don't really need to use finite difference. You just need to use a finite dimensional subspace. And that's very general in the numerics literature, right? Like it covers a broad class of methods. And what we end up showing is that like if you reduce your finite dimensional subspace to one that's somehow induced by a finite difference method, then it actually reproduces this notion of multisymplecticity. Okay. All right. But anyways, going on, these integrators, as I mentioned, were constructed kind of ad hoc. And the way they did that historically was to take symplectic integrators in time and space directions and kind of concatenate them. Okay. And so this is like the usual motif, like symplectic in time plus symplectic in space equals multisymplectic in space-time. Right, so the main classes of these integrators that are studied are multisymplectic partition Runge-Kutta methods, and then also multisymplectic spectral methods. And along with preserving the multisymplectic structure, one of the very interesting outcomes from this class of methods was that it was shown that the multisymplectic conservation laws somehow related to the dispersion relation for like dispersive wave phenomena. And it turns out that when you apply these methods, you actually preserve the dispersion relation in the sense that there's like some diffeomorphism between the actual dispersion relation and the numerical dispersion. And so you, in that sense, you get structure preservation for dispersion as well. Okay. Let me see. Okay, so this is the last background slide. Okay, so in 2013, my advisor and some of his colleagues introduced the notion of a generating functional for both Lagrangian and Hamiltonian PDEs. And it's essentially just a direct generalization of the type 2 generating function in mechanics. So the basic idea is that you prescribe, so you take some region in space-time U, right? And then here you prescribe like Dirichlet boundary conditions. So you prescribe the field values, whereas here you prescribe the normal momenta. So you use Neumann boundary conditions. Okay, so you essentially prescribe like the flux of the momenta across this boundary. Okay. And so if you do this, what you end up getting is some function which is known as the boundary Hamiltonian, which depends on the boundary conditions that you prescribe along one half of the boundary, the Dirichlet field boundary conditions that you prescribe on one half, and then the normal momenta boundary conditions that you prescribe on the other. Okay, and this serves as a type 2 generating function because what you can show is that if you take the derivative of this boundary Hamiltonian with respect to the field values on A, then you actually get the normal momenta values on A. And if you take the derivative of this boundary Hamiltonian with respect to the normal momenta on B, then you actually get the field values on B. So what you get at the end of the day is the following map. You get a map which takes the prescribed field boundary conditions on A, the normal boundary conditions on B, and you get a map that gives you the exact opposite. So the normal momenta on A, and then the field values on B. Okay, so compare this to the case of mechanics, which is like, right, we have Q0, P1 maps to, say, P0, Q1. Okay, so it's exactly analogous. Like in mechanics, you have some time interval, and you prescribe Q at the starting time, you prescribe P at the ending time, and then what you get is the opposite. Right, you get P at the starting time and Q at the ending time. So this is exactly analogous. The only thing we have to do is instead of considering some interval, we need a more general region in space-time. Okay. So essentially, the whole, I guess like the main thing of our paper that I'm going to talk about next is just to take this boundary Hamiltonian and discretize it. So the idea seems very natural. the main complications were just to work out the details, but the idea is pretty natural. Okay. And then I alluded to this before. The multisymplectic conservation law just follows from the fact that the squared exterior derivative of this boundary Hamiltonian is 0. Okay. All right. So now I'm going to get into the actual content of this paper. Any questions before I go on? Okay. All right. Okay, so we're going to want to think about Hamiltonian field theory, except instead of on some general region space-time, we're going to want to think about it on some kind of mesh. Okay, so we assume our space-time X is a polygonal domain, and let's say T of X is the associated mesh. Again, we're going to assume we have a trivial vector bundle, which is where our fields live. Okay, so for every element of this mesh, so every n simplex of this, well, n plus 1 simplex of this mesh, we introduce nodes on the simplex, and then we're going to introduce finite element spaces over these simplices. So if you're not too familiar with finite element theory, just think about this as like introducing some finite dimensional subspace corresponding to each simplex. Okay. And we're going to do exactly as we did with the type 2 generating functional, which is we're going to partition the boundary of each simplex into 2 distinct regions, A and B, where A we're going to think about as prescribing like the field values, and then B we're going to think about as prescribing the normal momenta values. Okay, and so we're going to define a discrete configuration bundle, which is just to look at all the nodes, Cartesian product with the vector space that your fields are valued in, and then a section is just a map from each node to the vector space. Okay, and so we denote that as phi sub I. Okay, so really we're just thinking about phi as like a map from I, which is the node, into into the vector space. Okay, so this is our kind of discrete notion of the configuration bundle. And then the restricted dual jet bundle is similar, where you also introduce the momenta for each node, and those are valued in the dual vector space, right, as in the continuum theory. Okay, so what are we going to do? We're just going to take all the continuous objects and approximate them. Okay, so we introduce some finite dimensional subspaces, and we'll also introduce some quadrature rules, which are approximations of the integrals that you see. So in general, you don't have to introduce quadrature rules, but it's nice to use quadrature because there's a lot of integrals that you can't solve exactly. And even if you can solve them exactly, it's not necessarily computationally efficient to solve them exactly. So you introduce quadrature rules to numerically approximate the integrals. Okay, so we're just allowing for the most general possible setup. But anyways, we're going to take all the objects of the continuum theory, discretize them appropriately, and then enforce the variation principle. And what we'll get at the end of the day is our class of integrators. Okay, so that's kind of the roadmap that we're headed for. So we take the boundary Hamiltonian, which was this expression right here, and we're going to just approximate this boundary integral over B, which is where we prescribe the normal momenta values. And then here's the action, and we're also going to approximate that. So that gives this expression here, where this approximates this integral, right? And then this approximates action, the action over your simplex. Okay. Okay, and then what we do is we enforce the variational principle. Okay, so this is the most general setting, which is hard to characterize explicitly, but what we'll do next is we'll talk about it on a rectangular grid. And on a rectangular grid, we can actually write out the equations very explicitly. Okay. All right. some reason my slides aren't changing on my screen. Sorry. Okay, well. So now we're going to assume that we have a rectangular grid, so we can kind of write out these equations explicitly. And we'll also assume that we have 1 + 1 space-time dimensions for simplicity. We consider higher space-time dimensions in the paper, but I think for clarity, I'll just do 2 dimensions. Okay, so let's assume we have a rectangular grid, and we're going to partition the boundary of each rectangle on a grid into 2 regions, A and B. So A is going to be like the bottom and the left edges, and B is going to be the top and the right edges. So the reason we chose this was analogous to mechanics. Like in mechanics, A is, for the type 2 generating function, A is like the left point and B is the right point. Okay, so this is like the analogous construction in higher space-time dimensions. Okay, and what we're going to do is along each direction, so the temporal direction and the spatial direction, we're going to introduce quadrature rules. Okay, and along those quadrature points, we're going to introduce the field values there and the momentum values there. Okay, and so that'll allow us to explicitly write what the boundary integral approximation is, right? So it's just given by quadrature over, so like this is what we want to integrate over, right? Integral B of PB phi B. Okay, so we want to approximate this integral, and if you associate quadrature rules, let's say like BI to each one of these nodes, sorry, quadrature weights, and then say quadrature weights B tilde alpha to each one of these nodes, okay, then what you get is that this integral is given by this quadrature approximation here. Okay, so here are these indices just to note like the momentum and the field values at the corresponding quadrature nodes on those edges. Okay, and the ones and the zeros, ones just mean at later time and space, and then zeros means at earlier time and space. Okay, yeah, I mean the indices for this is kind of messy, but it was hard to really think of a better way to kind of index everything. Oh, wow, I am coming up on time. Okay, so let me, sorry, I barely got into it. So let me just go through the salient points. So what we do is we reduce it to the finite dimensional subspace, we enforce the variational principle, and then we can improve some things really easily. Like for example, multisymplecticity just follows from the fact that the squared exterior derivative of your discrete generating function is 0. Exactly analogous to the mechanics case. Similarly, you have a discrete Noether's theorem. And I guess the last missing piece of the recipe was to actually say what the discrete action is. And for that, that's where we introduce some explicit finite dimensional subspaces. And the last thing we do is we show that if you use like nodally interpolating function spaces, you can rederive the class of multisymplectic partition Runge-Kutta methods. Okay. Yeah, and then the last thing we do is we look at family of Sine-Gordon Soliton solutions. And this is actually a really nice way to probe multisymplecticity, because if you look at the Soliton solutions, they just propagate in time. Like they propagate without changing form. So what this means is that if you look in phase space, which is like phi p0 p1, you know that you have this multisymplectic conservation law, partial 0 omega 0 plus partial 1 omega 1 equals 0. But it actually turns out that because the Soliton solutions are steady, that like this multisymplectic conservation law splits, and you get 2 symplectic conservation laws. So instead of looking at this 3-dimensional phase space, the family of Sine-Gordon solitons is a nice numerical example, because you can just look at both 2-dimensional phase spaces if you want to see if multisymplecticity is preserved by your integrator. Okay. So we did a simple test of like order 1 multisymplectic method and then a similar order 1 non-multisymplectic method, right? So they're the same order naively, and then we compared how they look in both of these phase spaces. So I'll just show the plots for the temporal direction, right? Because the spatial one is similar. Okay. So what you have is you have this family of sine-Gordon solitons, which are indexed by their speed. So we have 3 speeds that I chose, like 0.5, 0.47, and 0.45. And this is like the initial condition that we set for the simulation. Okay. And the reason we want to plot multiple families is a method should be multisymplectic if these families don't expand as your system evolves in time and in space, right? Like that's the definition of the preservation of phase space area. Like, so this separation shouldn't change at all. And actually it turns out because the sine-Gordon solitons are steady, that actually the curve shouldn't change at all. Like, normally you just need that the area between them is preserved, but because the sine-Gordon solitons are steady, like, the solution doesn't change at all. So here's at t equals 0, this is our initial conditions for the run. Here's at t equals 20. This is the multisymplectic method, and as I just mentioned, like the shape doesn't change at all. And these solid curves actually indicate the exact solution because we know the exact solution. And then on the other hand, this is the one using the same order method, but that it's not multisymplectic. And like the separation just gets like exponentially huge between them. Okay, so I'm sorry I rushed through like the main content. I didn't realize I was behind on time, but yeah, thanks for having me.
All right, let us thank the speaker.
Wow, an hour passes by really fast.
Yeah, it's ridiculous. Math talks are impossible. What was I going to say? Does anyone have any questions for the speaker? Brian, have you heard the term Wong-Zakai?
Not necessarily.
Oh, it's this way that you approximate the solutions to stochastic differential equations. And what happens is like you've got an equation and it's driven by like a regular vector field and then a noise piece, which is a stochastic integral. And what you do, and that's kind of what drives it, what you do is you approximate the thing that's driving the noise by some discretization. And the resultant thing is a simpler ODE. And then the theorem is that as the mesh of the discretization goes to 0, the simple solutions to those ODEs converge to the SDEs, the solution to the SDE. And this kind of strikes me as like, okay, you've got a system or a PDE that's kind of driven by a Hamiltonian or a multi-Hamiltonian, whatever you call it. And then what you do is you don't exactly discretize the Hamiltonian, but you discretize this action functional, which you could also kind of, or the generating functional. I guess you could argue that also drives the system. And then you get a situation where the solutions to the simple thing converge to the solutions of the hard thing.
I think that's a good perspective. It turns out if you just like discretize the Hamiltonian, you don't actually end up getting what you want. So yeah, you want to discretize somehow this generating functional that's like driving the motion rather than the Hamiltonian itself.
Oh, that's interesting.
Yeah.
Sweet. All right. Any other questions? All right. Let us thank the speaker once more.
Thanks.